Last time I left off talking about the wavefront set, and so in this video I'd like to give a little bit of background on what the wavefront set is and some initial definitions. So today we're going to be talking about the wavefront set, and I guess I'll start off talking a little bit about the history of the wavefront set. So the term was actually first coined pretty recently. So it was in 1971 by Hormander in a paper that I think was called, I'll abbreviate FIO, Fourier integral operators. And this is where he first, where the term wavefront set was coined. I think he gave credit also to, credit to Mikio Sato. Credit to Sato for, I think, a publication from 1969. So this is the guy that invented hyperfunctions, and the credit was given because I think there was a similar concept in the context of hyperfunctions, and Hormander adapted it so it could fit distributions, which that turned out to be the wavefront set. And so this is a concept that originates in pure math, actually. So this is not called the wavefront set because a physicist invented it. This is actually coined by Hormander, and the name wavefront set comes because of its utility in the study of propagation of singularities. So yeah, so we'll get into that maybe later. Okay, so at the time that this was invented, I'll talk about the utilities of the wavefront set. What they used it for at the time was to define more general operations on distributions. Namely, it was used to define, in some cases, you could define the multiplication of distributions. Given conditions on the wavefront set of the distributions involved. So you could do that. You could also, as I said, study the propagation of singularities. According to linear partial differential operators. Specifically, I guess in the beginning it was hyperbolic operators, wave equation and stuff like that. So yeah, study the propagation of singularities in a more refined sense. Not only where the singularities go, but what causes them. And to study regularity in general, not just propagation of singularities, but just to refine the study of the regularity of solutions. Of linear PDEs. Okay, so today these are still pretty active fields of research, but also this notion of a wavefront set and microlocalization has been picked up by physicists. So I can't speak much about those applications. Well, neither the other applications that I'm going to mention, but so in physics, quantum field theory and that stuff, I can just throw our own names, but I don't know what I'm talking about. In signal processing, so computer scientists and engineers have improved methods of signal processing because of the wavefront set. So to name a few specific cases, the tomography in its modern form is the algorithms behind it are made better because of the wavefront set, and let's say seismic imaging. And in math also. So in pure math, the direction, the research has branched out into many directions, but a few notable ones are that we have, so mathematicians have generalized the concepts that I'm going to be talking about using sheaf theory. Generalized sheaf theory. And now there are also cohomology theories based on microlocal analysis. So differential cohomology has also touched this field. Okay, so now that we have this this motivation, I think I'll start talking about the initial definitions. So first I'll define what it means to be, so let's start with the distribution first of all. So we have a U is a distribution on an open set omega in Rn. This is in Rn. And so we would like to define the wavefront set of this, but first we have to define what it means for this to be C infinity, or to be smooth at a point. At a point in what space? Well, we can consider this space here. So consider the space Cartesian product of omega with Rn. Now, we could consider manifolds. So omega could be substituted by an open set, say in a manifold. In Rn, this could be, the tangent space at that point. But we'll content ourselves with this for now. So we're looking in this space, and we would like to know that we'd like to define what it means to be C infinity at a point x0, xi0 in this space. So this x0 would correspond, this x0 would correspond to a position in the domain, and this xi0 would correspond to a direction in the tangent space at that point. Okay. So U is smooth at this point if we can say that there exists a phi, which is like a test function. I guess it's a smooth function with compact support that acts as a cutoff function. So if there's a phi of this type, a cutoff function around x0. What do I mean by that? So by a cutoff function, I mean that phi has to be equal to 1 in a neighborhood of x0, and 0 everywhere else. Okay, and it has to be smooth. So the existence, well, not 0 everywhere else, but it has to be equal to 1 in a neighborhood of x0. Then it has to decay to 0 within a neighborhood of that neighborhood, and then be 0 everywhere else. Talking about functions of this type here. So the existence of these kinds of functions is not obvious, but it's proven in any course on the theory of distributions. So so we can always basically find a function of this type. So this isn't the problem in the definition. So we ask for the existence of one of these, this phi. But we also ask another condition. This is the harder one to satisfy, such that if we multiply U by this phi, then it must be C. No, sorry. If you multiply U by this phi, then if we take the Fourier transform of this, if we take the Fourier transform of this, so this is now with respect to psi, then this has to decay. This has to decay rapidly. So this is going to be, let's say, I can write this as O of xi n for all n. So this Fourier transform has to decay rapidly along xi for all directions of xi. Okay. Now, what do I mean by all directions? Actually, so I didn't mean to say all directions of Rn. So what I mean here is all direction close to xi0. So we haven't used xi0 in this definition. We've used x0. So we've used x0, neighborhood of x0. We haven't used xi0. So for this, I mean for all xi in gamma. And what is gamma? Gamma is a neighborhood, a conic neighborhood, an open conic neighborhood actually, of xi0. So if we have xi0 here, so this is Rn. Let me draw this down here. So if we have Rn, say this is the vector xi0, then this would be, for example, an open conic neighborhood of xi0. So this I call gamma. And then I say that for all vectors in this cone, they must satisfy this over here. Okay. So there's an equality. I can actually make this more precise. So I can say that this actually has to be bounded by, let's say, a constant Cn times 1 plus the absolute value of psi to the n. I think it's something like this, yeah. So that has to be bounded by this. Right. So this is what it means for u to be C infinity in this direction here, this point in this direction. So now I can define the wavefront set. Wavefront set of u is simply the complement of these guys, of the points that are C infinity in this set here. So that's the wavefront set. And okay. So now I think we can do some examples now that we have the definition. So it's simply the set of points, and so this is like the set of points in the domain and the directions of the tangent space of that point, such that there is no neighborhood. There's no neighborhood of this guy where u is smooth. So that's the intuition behind the wavefront set. One initial example I can give is of the Heaviside function. So, example 1, or the Heaviside distribution. Heaviside function on R. So that would look something like this. So that would be 0 for all x less than 0, and we'll have a jump discontinuity at the origin, where it will now, the function will now assume the value 1 when x is greater than 0, greater than or equal to 0. Okay, this is the Heaviside function on R, and now we want to calculate the wavefront set here. So there's a result that we learned later on, that the projection of the wavefront set onto this omega here is actually the singular support of u. So here, I'll use that result, but it's you don't have to. It's easy without it, just to save us time. So the Heaviside function, it's clear that the singular support is only the origin, right? Because everywhere else it's just a constant function, so it's obviously smooth. So right here it's smooth, and here it's smooth. So the singular support is only the origin. So the wavefront set can only have as its first component the origin. So the wavefront set, let's call the Heaviside function h. Wavefront set of h has to be 0 and something else. Okay, 0 and something else. Now, so what do we have to do to determine if a direction is in the wavefront set? So now we're looking at directions. So in R, in the real numbers, there are only two directions. So there's only left and right. There's only left and right. Right, so these are the only two open cones that we have around originating at 0. So this is our first open cone, which is the positive numbers, and our other open cone is the negative numbers. So we only have to check these two directions. And now let's check then if h is smooth along these two directions. So what we had to do is, so according to the definition, we have to see if there exists a cutoff function around x0 such that it equals, so it's a cutoff function around x0 such that the Fourier transform decays rapidly in the direction that we want. So let's check each direction. So first we have to take a cutoff function. So let's take a function that looks like, this around the origin here. So this is 0, this is the origin. And if we multiply anything that looks like this by the Heaviside function, what that'll look like. So intuitively, I won't multiply this out. I won't do the actual calculation, but you can see that the multiplication of these two guys is going to be something like, so for the first part, we have just 0, so it's going to be 0, 0, 0, 0. Then we have the point where the cutoff function increases to 1, but the heaviside function is still 0 at those points, so it'll be 0, 0, 0. Yes, okay, 0, 0, 0. And at this point, we'll still have the jump discontinuity because the heaviside function jumps here, and our phi, call this phi, is equal to 1 at this point. So what predominates here is the behavior of the heaviside function. Here, what also predominates is the behavior of the heaviside function, as long as phi equals 1. And let's say at this point, phi starts to drop off, and so this will happen because the heaviside function is 1 here. So this is what it'll look like. We'll still have that jump discontinuity at 0, and both sides will still be smooth. Okay, so we would take the Fourier transform of something like this. Right, so the Fourier transform of something like this, I'll make a guess. So I won't do the calculations, but I will make a guess that the Fourier transform of something like this is probably very similar to the Fourier transform of a function that's 0 here, then it suddenly jumps, and then it's 0 everywhere else. So it's, I guess engineers have a name for this, maybe an impulse or something like that. It's a part of a square wave, I guess. So it's 0 everywhere, it's 1 at this interval. It's a characteristic function of an interval, right? So because we can choose phi with this part as small as we want. So that's also another theorem in distribution theory. We can choose phi with this part here as small as we want. So this is practically this. Again, this is not a rigorous argument by any stretch of the imagination. But so if this kind of looks like this, we can apply the Fourier transform. And well, we know the Fourier transform of a function like this, and that is a function like this, which would be maybe I would say, yeah, I guess a constant plus a constant C1 plus another constant times sine of, let's say, another constant. I'm just gonna go crazy with the constants here. Plus C4, it's another constant. I'll divide all this by x. What I mean is it basically looks like sine of x over x, right? So what matters is the asymptotic behavior of this. So does this decay rapidly at infinity? And the answer is no. This actually looks like it behaves like O of 1 over x. This behaves like 1 over x at infinity, which is not what we want. So this is not C infinity. So h is not C infinity. H is not C infinity at the point 0, and I guess I'll choose 0, 1. Not C infinity at 0, 1. But could it be in the other direction? Well, the other direction is the same thing. It's kind of a symmetric argument, so it's not at any of these points, either 0, 1 or 0, minus 1. So the singular support, is 0, and we found that it is not C infinity at any along any direction. Not C infinity along any direction. So both of these directions, both of these cones are actually, so the left cone and the right cone are both in the wavefront set. They're both in the wavefront set. So going back to this definition here, the wavefront set, we can put here 0, and then as for the directions, I'll just do, I guess, xi, where xi is just not 0. So any direction works here. So this was an example in R. You may be asking, what is asking for an example in Rn? Right? Because in R we only have 2 directions. Not that interesting in Rn. It's the first dimension where we have infinitely many directions. So in Rn we can take, for example, the delta, the Dirac delta, at 0. So that would be, so if you were to look at it as a function, it would be 0 everywhere except at the origin where it's infinity. You can define this rigorously using distributions. So this is our example in Rn. The Dirac delta centered at 0. So now let's try to calculate the wavefront set of this guy. So again, we start the same way as the other one. So we note that the singular support of delta is 0, or at least 0. Could be nothing, but we know it's 0 because delta is constant. It's a C infinity function around any other point that's not the origin, and around the origin there's this massive singularity. So this is the singular support is 0. So that's the only place we really have to look for the wavefront set, or for the directions now of the wavefront set. Okay, so let's do the same thing now. So we take an arbitrary test function. So we take phi, a cutoff function, sorry. So phi cutoff function around 0 now, around the origin. And now we would like to take the Fourier transform of this and analyze the decay in all directions. So we can call this, so we take phi, and now we multiply delta with phi, take the Fourier transform. And what is this going to be? Well, we know that, first of all, delta times phi, that's just delta, because phi is equal to 1 in a neighborhood of delta, and delta is 0 everywhere else that's not the origin. Okay, so this is just delta. So you can check this using distribution theory. So this is just delta. So what we're looking for is the Fourier transform of delta. But we know the Fourier transform of delta is a constant, and a constant certainly does not decay rapidly at infinity. So this just behaves like a constant at infinity. So it does not decay rapidly. Does not decay at all, actually, at infinity. And so no direction here is going to be a part of our smooth set. So again, we're in the case where every direction is in the wavefront set. So the wavefront set is the same as this above case here. We have the point is the point in the domain is 0, and then in the tangent space we can choose any point we want except the origin. So now we can move on to let's talk about a few properties. So a few initial properties of the wavefront set. The first one that I like to talk about is that it's closed. So given any distribution u, the wavefront set of u is closed. Now, so what does it mean to be closed, first of all, in omega times Rn? Well, in the product topology, for you to be closed in this set, you just need to be closed here and closed here. But by definition, the wavefront set is just the complement of the points where we use is C infinity, points we use smooth. And in the definition of this guy, to determine if a point to determine if this first component here, is in this C infinity set, what we had to do was localize. So we had to multiply. We had to choose a neighborhood first of all. Choose a neighborhood. So the question we asked is x0 in, let's say, in this smooth set. Okay. What we'd have to do to answer this question is choose a neighborhood. Choose a neighborhood of x0. Take a cutoff function with respect to that neighborhood. And then we would take the Fourier transform. Okay, so let's draw this out. What's going on? So we have x0. We took a neighborhood of x0. So this is v. And then we took the Fourier transform of this guy. So note that if we had taken an x1 here, and we could have chosen the same v as the neighborhood of x1. Could have chosen the same v, and this same v would have contained x0. So the Fourier transform of the function of the distribution u, let's say phi times u, where phi is a cutoff function with respect to v, is going to be the same. Is going to be the same for, because you've chosen the same v. So this definition actually doesn't depend. It doesn't depend on the point. It depends on the neighborhood v. So using this argument, you can show that that this, at least in the first component, that in the first component, so what do I say? The C infinity set of u is open in the first component. And so to show it's open in the second component, it's a similar argument, because for a direction now size 0 to be in the smooth set of u, there has to be, the requirement is that there's an open cone around this direction, such that all of these guys, all these other xi's, are also in the smooth set. So again, this definition does not depend on your choice of psi. It depends on your choice of open cone gamma, right? So again, you can use this argument to show that the wavefront set, or that the C infinity set of u is open in the second component. So you combine these two, and then you show that the wavefront set is closed. So I won't go into more detail, but you can prove this rigorously. So another thing is that the wavefront set is a conic set. Now, what does it mean for the wavefront set to be a conic set? It's that, so we know what a conic set is in Rn. It's a set exactly of this type over here, right? That if we have any vector inside the set, multiply it by a positive scalar, it's still in the set. It's closed under multiplication by a positive scalar. But what does it mean to be conic in this set? Well, it's the same thing. It means that, so for it to be conic in this set, it means that if you fix an x0, so if it is conic, meaning that if, so let's write this formally, if x0 xi0 is in the wavefront set, then x0 times lambda xi0 for lambda positive is 2. So it just means that if you fix the first component, you only have conic sets in the second component. So yeah, and here, so forget that this is here. So this is just the definition of being conic in that set, and the wavefront set is in fact conic. Because remember, in the definition of the C infinity set, a direction was in the second component of the C infinity set, so psi 0 was in the second component, if there was an open cone around it, such that the Fourier transformation of this guy here decays rapidly in gamma, which is this cone. So the wavefront set is conic because if you take any positive scalar and multiply this vector by any positive scalar, so this is gamma times psi 0. Note that gamma, this is lambda times psi 0. Note that gamma is still an open cone around this guy. So nothing really changed in the definition. The definition is, so if this guy's in the C infinity set, so is this larger guy or smaller guy, or anyone in the same direction. So what's not necessarily valid is that the wavefront set is a double conic. So it doesn't necessarily extend backwards like this, which is something you might think intuitively in the beginning because, well, it's in the same direction as the other vectors. But then you realize that the Fourier transform, I guess if you consider from functions to functions, so Fourier transform from L2 to L2. Now, but in distributions, the distribution of Fourier transform is it generalizes this Fourier transform, so it's the same as the classical transform in the classical case. So let's look at the classical Fourier transform. It's an isomorphism between L2 and L2, and there are in fact functions. So let's say Fourier transform goes in this direction. There are in fact functions that you can take here. That are not symmetric with respect to the origin. So let's say in R, if you're in R, there are functions that look like, for example, that maybe they decay rapidly along this right side here, but along this left side they don't decay so rapidly. So if we take the inverse Fourier transform of this, that would lead us to a function that when I take the Fourier transform, it decays rapidly in one direction, but not the other necessarily. So this is probably correct. I haven't thought this over too much. I haven't done this exercise, but you can probably find an example like this. So this would be in R, but in Rn there are also probably examples, counterexamples to the wavefront set of not being a double conic, right? So we know it's a conic, but not necessarily does it extend backwards. So I still have to do that calculation. I'm not sure about that. If anyone can say in the comments whether this is true or not. Okay, so talking about so the wavefront set is closed, it's conic. Right, so there are a few other properties that I planned on talking about, but I'm running out of time here. So I think I'll briefly mention, so talking about these initial properties, there's another initial property that's very important, though the proof isn't exactly short. It says this. So we've used it in the beginning, which is that the projection, the projection of the wavefront set of U is equal to the singular support. Singular support of U. And by projection, I mean projection onto the first component. So this should be equal to the singular support. And I won't prove this here, but one direction of this is pretty easy if you have a certain lemma. And the lemma is pretty intuitive actually. So one direction is that, yes, this direction here. So this inclusion here, that the projection of the wavefront set is contained in the singular support. We can prove that direction if we know that the pretty intuitive lemma that x0 is not in the singular support. Oh, here I wrote subsing. I never know subsing or sing sub. I'll write subsing. So this is not in the singular support if and only if there exists a phi in C infinity C of omega. So a cutoff function around x0 such that phi times u decays rapidly. In all directions. And to prove this lemma, it's just a direct application of the Paley-Wiener theorem. And I say it's intuitive, obviously, only if you know the Paley-Wiener theorem. Yeah, so that gives this very important result, which we use all the time, and that I used above. The projection of the wavefront set is in the singular support. And so another property that'll turn out to be useful, and maybe I'll prove in the future, is that it's a sort of pseudo-locality for the wavefront set. And what I mean by that is, so if I have P, a linear partial differential operator, then the wavefront set, so I'll just write that. then the wavefront set of P of U, so use the distribution, is contained inside the wavefront set of U. So it says that P does not increase. I guess I can. Yeah, P does not. What can I say? Does not create singularities, maybe. So this is a very important theorem in because it just displays the power of wavefront sets in this application, which is what we want to apply it to, which is the analysis of linear partial differential operators. This is a very nice result. P does not create singularities. Singularities in the sense of the wavefront set. Doesn't increase the wavefront set. And so we have other results now applying to linear partial differential operators. Another one is that, so I won't even give kind of an intuitive statement on this. I'll just say a few words about it, which is that there's another result. This is very important, that it tells you that if P is not, I think I'll stop the video with this. This will be the teaser for the next one. Maybe I won't get to talk about this in the next one, but at some point I'll get to it. The result is that if P is not hypoelliptic, then the characteristic set is to blame. So I think I'll just leave that written as it is. And yeah, I'll end the video here with this mysterious statement. And next time we'll probably talk more about wavefront sets.